Okay, so we've been talking about excuse me, been talking about solutions, and remember, basically a solution, and obviously we will be before we get into that, I guess, we'll be doing a little lecture. We will be stopping a little bit early, and then obviously we'll be taking the quiz at that point on through Canvas and Proctorial. So we'll get going here on the lecturing part. So we were talking about solutions, and remember, basically, a solution is, if it will right, there we go. Solutions. Solutions are really those guys that do you get that aqueous symbol? And basically, it's a homogeneous mixture. And as we talked about previously, there is a difference between a solution that's the aqueous symbol and something that has like just the L symbol next to it. Again, something with a L symbol is a pure liquid. Like I think the example we used was just pure water by itself would be a pure liquid. If we take something, for example, and dissolve it into water, we typically will make a solution, something like, say, sodium chloride. And a solution really is made up of two parts. It is the solute, which is the smaller part of the solution. So, for example, in the sodium chloride example, it would be the sodium chloride. And the larger part of the solution is the solvent. And that would be the larger part with an L, the larger part. And again, if we took something which was a sodium chloride solution, again, the sodium chloride or the name of the solution would be the solute. And again, in this particular case, water would be the solvent. As we talked about, there are certain things that are soluble in each other, which means they really do mix. And something like water, which is polar, as we talked about last time, works really well for things that are polar, for things that are ionic. They're able to use those intermolecular forces and really interact really well with one another. Now, again, water is not always the best choice, as we talked about last time as well. If you had something that was non-polar, say something like Cl2, that is a non-polar guy. We would want something that would be non-polar, and that's because they both would also be using dispersion forces to sort of mix and interact with one another. So there's that idea that we talked about in terms of solubility of like dissolves like. So things that have similar types of interactions with themselves and others are sort of soluble in each other. So what that really means is typically if we have something that is polar and polar, they're all good. They're going to be soluble in each other. We got something that is ionic and polar, which is really what happens in sort of this example. Sodium chloride is ionic, water is polar, the waters surround the sodium chloride, the sodium ions, the chloride ions, and that's what helps it dissolve. Also, sometimes missed by people is the idea that if you have something, again, that's non-polar and non-polar, those guys are going to be good to go with each other as well. It's really only kind of when you cross over in terms of polarity. If you take something that's polar and non-polar, they really aren't going to mix. So I think we saw oil and water, for example, oil being polar, water, obviously, I'm sorry, oil being non-polar, water being polar. And obviously they just kind of layer on each other. You see those kind of layer of the oil up on top rather than mixing. And that's that idea of like dissolves like that we talked about. We also talked about last time solubility rules and using sort of solubility rules to decide, whether or not if we sort of mix these two things, these two ions, for example, and they come together to form an ionic compound, will they make a precipitate or not? And there's several solubility rules that we looked at, and that can help us decide whether or not, again, in a certain type of reaction, like a double displacement reaction, when those two ions come together, would we expect it to be soluble, which would get the aqueous symbol, or would they be a solid form, which would get obviously our precipitate form, which would get a solid or S sort of symbol next to it. We finished up, I think, talking here about electrolytes. Electrolytes are really substances that when they do go into water, for example, They tend to break apart into ions, and the breaking apart into ions are really important for sort of the function of electrolytes. Electrolytes can basically conduct electricity really well, and it's those presence of those ions which help kind of complete the circuit that allows it to do that. So something that's a strong electrolyte will 100% break apart into ions. So for example, on the top there, we got sodium chloride. When that's really in solution, you have no NaCl sort of units still together. They have 100% broken apart into all sodium ions floating around, all chloride ions floating around, as we can kind of see here in this picture. And what that does is it allows really sort of electrons and everything to be moving really well, and it conducts electricity very, very well. And the light bulb example is usually used a lot. The light bulb will go off very brightly because it's able to conduct electricity very, very well. There are certain things that are weak electrolytes, like in the middle here. And these weak electrolytes are things that actually, when they do go into solution, unlike a strong electrolyte, they actually tend to stay together. So HF, which is hydrofluoric acid, is an example of a weak electrolyte. It will mainly stay together in solution, but it still will break apart a little bit into ions. So you'll get a little bit of H pluses floating around, a little bit of F minuses floating around. So since it's still able to produce some ions, is able to conduct electricity, but is not able to conduct electricity anywhere near a strong electrolyte, as we can kind of see from the brightness of the strong electrolyte light bulb versus the weak electrolyte light bulb, kind of dim. The other sort of recognition of something being a weak electrolyte does lie within the arrows. On weak electrolytes, we do see these reversible arrows. Again, arrows basically heading in two directions, which means the reaction goes one way and then can come back the other way. And that's very different than the arrow we see in a strong electrolyte. It's basically like a one-way arrow. There's nobody else coming back the other way. So that's a major way you could kind of recognize the difference between sort of a strong electrolyte and a weak electrolyte is actually those arrows. There's also non-electrolytes, which is our last guy down here. And our non-electrolyte will basically dissolve in solution, but the difference is it will not produce any ions. So really the lack of ions being produced is the reason why it will not conduct electricity. There's kind of no ions present, even though it can dissolve, for example, like sugar. But sugar is a covalently bonded sort of molecule sharing of electrons, no ions that are formed. So we would not get any ions. No ions means, again, no electricity. No electricity means obviously the light bulb there would not go off. Any questions on that stuff we talked about last time? So continuing on then, we're going to talk a little bit about equivalents, and sometimes equivalents are used, for example, in IV bags and things like that. They're used as sort of a unit of concentration. So sometimes we do use equivalents for a unit of concentration for a solution. And typically there's kind of two sort of equivalent type concentration units we sometimes come across. One is equivalents per liter, or sometimes we do what's referred to as I'll spit that out, milli equivalents per liter. And these are two common units that we sometimes use. In case you're curious about sort of the relationship between these two, it's basically kind of the same thing as milliliters and liters. There's 1,000 milli equivalents and then one equivalent, sort of the conversion there. And again, that's kind of similar to there's 1,000 milliliters in 1 liter. So same idea. It's really the milli sort of prefix there. So an equivalent is really the amount of ion that's equal to 1 mole of positive or negative charge that we see. So we kind of, for the most part, use equivalents as sort of conversion factors. And we really could get the conversion factor from the actual ion that's present. So for example, if we had a barium ion, the barium ion has a +2 charge. And what we could say is in 1 mole of a barium ion, there would be 2 equivalents. And the 2 again comes strictly from the actual number of the charge. Doesn't matter if it's positive, doesn't matter if it's negative. It's actually just a number here in this case. It's important. If we had something like sulfate, SO4 2 minus, we could say in 1 mole of sulfate, there would be 2 equivalents. Again, the 2 coming from the actual charge. You know, if you had phosphate, 1 mole of phosphate gives you 3 equivalents. Again, the 3 coming from the number here in the charge. And just like sort of any sort of equality here, we really could use these as conversion factors. So for example, you could say in 1 mole of barium, there are 2 equivalents. Or we could use it as the opposite conversion factor, 2 equivalents in 1 mole of barium. Same idea with our phosphate, our sulfate here, I'm sorry, 1 mole of sulfate, again, would give us 2 equivalents. Our 2 equivalents would give us 1 mole of sulfate. So again, we sort of use this as a conversion factor. And again, it's not necessarily anything to do with, say, the positive or negative part of it, of the charge, but it is actually the number here. Again, that's sort of important. So let's take a look at sort of a problem, kind of like where we'll perhaps do some conversions using equivalents. So let's say, for example, we had let's say we had 0.025 moles per liter of something that is potassium sulfate. And we want to know what is the equivalence per liter and milliequivalents. Try that again. Milliequivalents per liter for all the ions that are present. So in this case, there's potassium ion present, and there's also sulfate ion present. So when we would do this, the first thing we'd want to really kind of figure out is, you know, what is the relationship between the whole thing here and each of those ions. And we could do that by simply taking our potassium sulfate and thinking about what happens when this guy basically goes for a swim. When this guy goes for a swim, it's really a strong electrolyte, which means it's not going to stay together. And we would get actually 2 potassium ions, and that 2 comes from here. And we would get 1 sulfate ion that basically would come across. And we could use that to help us convert from moles of the whole thing to moles of each of the individual ions. So for example, we'll start with potassium here, and we could say that there's 0.0250 moles per liter of the whole thing. And just looking at that relationship, we could see that for every 1 mole, kind of like stoichiometry, every 1 mole of the whole thing, we get 2 moles of just potassium. And we could do that conversion. So 1 mole of the entire thing gives us 2 moles of potassium ions. The moles of the entire thing will cancel, and that will give us 0.05 moles per liter of just the potassium ion. So we're kind of using the formula to go from the whole thing to just the potassium, because again, we're interested in just the potassium by itself. Any questions on that so far? We also are interested in just the sulfate by itself, so we could do the same type of calculation. to get us to just the sulfate. So 0.0250 moles of the entire thing per liter. And again, from the actual way it breaks apart, we can see for every 1 mole of the entire thing, we produce 1 mole of just the sulfate. And we could use that as our conversion factor here. And we will end up with 1 mole of the whole thing on the bottom, so it cancels, and 1 mole of sulfate up on top. Gets rid of the whole thing and leaves us with, not that number, leaves us with 0.025 moles of sulfate per liter. So really all I've done here sort of right at this point is, because I'm not really interested in the whole thing by itself, I'm interested in each of the individual ions. I'm just trying to get it from the whole thing to each ion and sort of have the concentration that we're looking for. Now we could actually get to the part where we're going to change it to equivalents per liter. So if we look at where we are right now, we don't have a lot that we need to change, because on the bottom is liters and we are looking for liters. So that part is fine. The only thing we really need to change is to go from moles to milliequivalents, are either equivalents. So we have liters here as well, to equivalents. So to do that, that is where we use the relationship that we just talked about. So we know that K plus has a +1 charge, which means we could say for 1 mole of potassium ions, there's 1 equivalent. We could also come up with that relationship for the sulfate as a -2 charge, which means 1 mole of sulfate will give us 2 equivalents. Again, we could use both of these as conversion factors to convert to what we need. So I think what I'll do is I'm going to carry these numbers over to the next page here, and then we'll continue on that slide, I think. 0.05 and 0.025. So we have 0.05 moles per liter of potassium, and we had 0.0250 moles per liter of sulfate. Okay. So using our equality that we saw before, we could say that 1 mole of potassium, which would go on the bottom, would give us 1 equivalent. And again, because potassium is +1, that's going to allow the moles to cancel. And I will end up with 0.05 equivalents per liter of potassium. Any questions on that so far? Now, that was one answer we were sort of looking for, which was what is the equivalence per liter of potassium? But we also wanted milliequivalents per liter. So we could use that relationship that we talked about a second ago, that 1,000 milliequivalents is equal to 1 equivalent. So we could do a conversion here at the back end, and we can use that. I'll just kind of pick it up from here. In 1 equivalent, there is 1,000 milliequivalents. The equivalents would cancel, and if we multiply that by 1,000, we will end up with 50 milliequivalents per liter of potassium. So these are really, be honest with you, these are really 3 different ways to express the concentration of potassium in this particular solution. This, as we'll talk about shortly, is what is known as molarity. which is moles per liter. This is equivalence per liter, which is a unit of concentration. And this is milliequivalents per liter, which is again also a unit of concentration. Any questions on that calculation on top there? We can also do it for the other ion that's in this solution, which is sulfate. At this point, we will convert it from moles per liter to equivalents per liter. And in 1 mole of sulfate, because the charge here is 2 minus, that actually gives us 2 equivalents. The moles of sulfate cancel, and we end up with 0.05 equivalents per liter of sulfate, which would be our other answer we were looking for. We also can then convert it into milliequivalents using that conversion factor. And again, same conversion factor there, 1,000 milliequivalents per equivalent gives us 50 milliequivalents per liter of sulfate. Any questions on that calculation there? You might notice a couple of things like the concentration equivalents per liter for our potassium is the exact same as our sulfate. Also for milliequivalents per liter, they're exactly the same. So why is that? It is because when we put together an ionic compound like potassium with sulfate, we want to balance out the charge, which means we need 2 potassiums for every 1 sulfate. That gives us our K2SO4. And we always balance out the charge with ionic compounds. So technically speaking, when we talk about a concentration that's based on charge, which is what equivalents per liter and milliequivalents per liter are, we basically have balanced out the overall charge in that particular solution. And that's basically what we see here represented by these numbers. So if you calculate equivalents per liter or milliequivalents per liter for a solution, they should always end up being the same concentration, the positive guy that's in the solution and the negative guys in the solution when you're doing equivalents per liter and milliequivalents per liter. Again, because it's really based on the charge. And the idea of an ionic compound is we put it together to balance out the charge, which means we should technically have the same sort of charge sort of concentration for each of the ions that are floating around. Any questions on that one there?
Professor, I have a question on the previous slide. Page.
Let me back it up there. This one?
Yes, on the middle section where you got no, the third row, it's
Right
1
here.
mole SO42. The one below that one.
Oh, the one below that, right here?
Yes. So how'd you get the 2 moles? I'm a little confused on that because I thought they were supposed to cancel out. Usually it doesn't happen that way.
I just want to make sure. Are we talking about this part of the calculation? Right
Yes,
here?
yes.
Are you asking how I got the 1-to-1 relationship here?
Yes.
Yeah. Okay. Yes. So basically, when we take something like potassium sulfate, for example, I'm just gonna draw it over here. I think. Let me see. That's right here. So when we take something like potassium sulfate and we dump it into, like water in a solution.
Yes.
Basically, this is what happens. For every one of those that we dump in, we get basically 2 potassiums and we get 1 sulfate that basically comes from this formula when it breaks apart.
Okay.
And that's how we get those relationships by saying for 1 mole of the entire thing, as you can see, when we dump it into here, we basically get 2 moles of the potassium ions that come out.
Yes.
But we only get, for every one of these, 1 mole of the sulfate that comes out. And that's where those kind of conversions come from. Is basically, how many of each of those ions you get per kind of unit you drop in there. So every one you drop in there is going to break apart. In this case, we get basically twice as many potassiums than we do for the sulfate. And that's why when we look at the concentration, which is not based on charge, the first one here, which is really the molarity, we see we have twice the concentration of potassium than we
Yes.
do sulfate. And that's why basically it's like a 2-for-1 deal for potassium versus sulfate.
Okay. All right. Thank you.
Welcome. Other questions? Okay, so maybe there is. So again, basically we can figure out the sort of conversion factor really from the charge. And again, it doesn't matter if it's positive or negative. It just really matters in this case, the number. So for example, here is iron. We could come up with for every 1 mole of an iron 3, we would get 3 equivalents. And this is a lot of times how we use it. We haven't talked about molarity yet in this chapter, getting to there, but it basically is that moles per liter. So we kind of use it as a conversion factor to go from molarity to equivalents per liter, and then, to milliequivalents per liter. So we really just kind of pull that conversion factor from the actual number of a charge. You can really just think of it like dimensional analysis. You want to kind of get rid of the units you don't want, kind of keep the units that you do. Any questions on that there? So then let us get into some other types of concentrations for solutions, maybe more of ones that we will kind of use a little bit more often than probably equivalents per liter and stuff like that. The first one is mass percent. And this is sometimes also abbreviated as percent mass to mass, which is what the M's mean. And it's the mass of the solute over the mass of the solution times 100%. The really important part of this sort of formula is actually the bottom part here. Remember, as we talked about a second ago or a little bit earlier there, a solution is really made up of 2 parts. It's made up of the solute and the solvent. So you want to make sure that when you do the bottom part here, that you actually have both of those values sort of given to you, or you're using the correct value. And what I mean by that is oftentimes in these problems, they will sometimes just give you the solvent and the solute values separate from each other. So they'll kind of be separate from one another. So you sometimes need to add them together to make sure you actually get the whole entire solution. It's very common that sometimes people will just take the solvent rather than the entire solution. And again, in these type of problems, sometimes we do see it sort of broken up. We also, if we had a percentage given to us, like if we said, hey, this was 4.5% by mass sodium chloride solution, we could turn this into a usable conversion factor by assuming 100. And we assume 100 because that keeps the numbers the same. Like if you got 4.5% on your exam, hopefully not, that means you got like 4.5 points out of 100. So we can actually turn this into kind of a usable conversion factor by going 4.50 grams of sodium chloride in 100 grams of solution. Or we could use it as the opposite way. In 100 grams of solution, there would be 4.50 grams of sodium chloride. So sometimes you may be given the percentage by mass. And again, it's sometimes easier just to kind of convert it into a conversion factor and sort of use it that way. So let's take a look at one here. So why don't you take a second here. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent? So again, here we're looking for percent mass to mass. So take a minute or two and see what you come up with. Divided by the mass of the solution times 100%. So we basically want to kind of identify some things. So we have 2.5 grams of calcium chloride mixed with 50 grams of water. We know that this looks like the smaller substance. which means really this is our solute, the calcium chloride here. And obviously the water here would be our solvent. So the mass of the solute we have, that is obviously the 2.5. We do not have the mass of the solution. So as I mentioned before here, this is actually given to you separate. So we do actually need to add those together to make sure we get both parts of the solution. Again, the solute, which in this case is 2.5 grams, and the solvent, which is 50 grams. Again, here you would not want to divide by just the 50 because that would be just the solvent and actually not the entire solution. So again, that's what I was speaking about before. It's very common. People will just divide by 50, but you actually do need to add these together to make sure you actually get the solution, which is really what we need for the bottom. Now that we really have both of those numbers, the percent mass to mass would equal our 2.5 grams up there on top. Our bottom would be our 52.5 grams times 100%. Looks like perhaps a 4.76% by mass is typically how you'd probably leave it in terms of units. That's kind of the grams would cancel, and probably lay up calcium chloride there as a way of doing that. Any questions on that calculation? So again, very commonly, the solution is sort of broken up for you in these type of problems. They very often will give you that kind of solute and solvent values separate. You want to make sure that you get them to the solution so you get it correctly. So let's try another one here. What is the mass of hydrochloric acid that's contained in 35.5 grams of the hydrochloric acid solution here? I'll add that for you. All right, so see what you come up with. We're actually looking for the mass of the hydrochloric acid in this particular case. Our formula we just saw is our mass of our solute divided by the mass of the solution times 100%. The solute here is the HCl. Remember that the name of the solution is always the solute. So when we're looking for the mass of the HCl, that would imply that we are looking for really the mass of the solute in this particular case. So that means that they did give us the percent mass to mass, which in this case was 37.2%. We also have the mass of the solution, which is 35.5 grams. And again, you could plug and chug into this equation and solve for it. You also could take a more dimensional analysis approach and use this as a conversion factor. So we'll go that way here, just again, show you how to do it perhaps a different way. That might be helpful. If it's 37.2% by mass hydrochloric acid, what that means is you have about 37.2 grams of hydrochloric acid and 100 grams of solution. Or you could use it the opposite way. In 100 grams of solution, you would have 37.2 grams of hydrochloric acid. Again, we could assume like 100, so the numbers stay the same. So if we kind of did this using this as like a conversion factor, we could start with the 35.5 grams of the solution. Here we would want to use the conversion factor here on the left, where we would have 37.2 grams of hydrochloric acid and 100 grams of solution. The grams of solution would cancel each other out, and we would take 35.5 times 37.2 and divide it by 100, gives us 13.2 grams of hydrochloric acid in this particular case. So this again is a more dimensional analysis approach. Honestly, if you just plugged and chugged it into the equation here, you had this number, you had this number, and you had this number. Basically, when you rearrange that, it's the same math you would be doing here, because you would be putting 37.2% equals the mass of the HCl divided by 35.5 grams times 100%. We would be dividing, oops, if I don't hit the wrong button there, I'm not sure why I just hit there. We would be dividing the 100 to the other side, and we would be multiplying the 35.5 to the other side. And basically that's what we just did there, 35.5 times 37. And we divided by 100. So mathematically it works out the same, but sometimes it might be a little bit easier to see if you kind of take the dimensional analysis approach, but you could definitely, if you want to, just plug and chug it into the formula as well. Any questions on that there, or mass percent? Okay. So what we'll do is I think we will stop here, give everybody a chance to